Hi, my name is Yangzheng. I will be presenting our paper today, Learning Better Key Points for Multiple Objects Six-Stop Pose Estimation. Within the field of computer vision, key points are predefined points or pixels to represent distinctive features of target objects. This concept is frequently employed for feature extraction and representation in diverse tasks, including object and skeleton detection. In recent six-stop PE methods based on machine learning, two key point-oriented categories emerge: keypoint hypothesis-based methods and keypoint voting-based methods. Methods falling into the keypoint hypothesis category typically produce heat maps or probability scores, employing a non-maximum suppression style to localize the key point. On the other hand, keypoint voting-based methods estimate intermediate voting quantities such as radial distance, vector, and offset. These computed votes are subsequently casted into a voting space to determine final keypoint location. For keypoint voting-based six-stop PE methods, keypoints are typically sampled using two main approaches, FPS and bounding box. Both algorithms ensure that the sampled keypoints are sufficiently spaced apart, enhancing the performance of front-end least square fitting algorithms like PMP. However, these algorithms have not considered the training of the backbone network. Our proposed KeyGNet addresses this oversight by optimizing the keypoint locations, allowing the associated votes to be better learned by the backbone network. Here is a visual example illustrating the histogram distribution of three key points sampled using FPS and bounding box. The radial voting quantity representing the gradient distance from object points to key points is employed for simplicity. This choice is due to its single dimension, making it easier to visualize in a histogram compared to offset and vector, which necessitate at least two dimensions. The Wasserstein distance between these key points histograms are also calculated. As illustrated in the third histogram, key points sampled using bounding box with minimum Wasserstein distance exhibit more uniformly distributed votes, indicated by a more similar contour of the histogram compared to the first and second histograms. The majority of the backbone networks employed in six-stop PE adhere to a classification structure. If the votes from the first and second histograms were learned by such networks, they might encounter a similar imbalance level issue in the classification task. In contrast, the votes in the third histogram could be learned more effectively in comparison to the others. We thereby propose KeyGNet, a network that learns features extracted from segments of target objects in real scenes to estimate the set of optimized key points with similarly distributed votes. Our KeyGNet is based on the graph convolution network EdgeConv, which is designed specifically for point clouds. The input of the network is point cloud segments of our targeted objects with RGB values. The output of our network is optimized key points. Our network is supervised by two loss terms, a Wasserstein distance loss for the histogram similarity measure and a dispersion loss for key point sparseness measure. We test our KeyGNet key points on three key point voting-based methods, including the radial voting-based RCV pose, the vector voting-based PVNet, and the offset voting-based PBN3D. Our experiments are conducted on all 7 BOP core datasets, which contains the commonly used Occlusion LINEMOD and YCV video datasets. We evaluated the performance by using the BOP average recall matrix. We also report the ADDS performance for LINEMOD occlusion and ADDS AUC for YCV video to compare with the heuristic FPS and bounding box key points. Table 1 presents the outcomes of the Bob AR assessment. MIMO signifies multiple instances of multiple objects, and SISO denotes single instances of single objects in a scene. SISO was the initial mode for all three methods due to the observed performance decline when converting from SISO to MIMO. Notably, our KeyGNet key points not only enhance the performance in both SISO and MIMO modes among all three methods, but also eradicate the SISO-MIMO performance gap. Our performance improvement for all three methods tested in MIMO mode made it possible for these methods to simultaneously estimate accurate poses for multiple instances of multiple objects in a scene with a similar speed compared to the SISO mode. By using KeyGNet key points, RCV pose performance on LINEMOD occlusion is even improved in MIMO mode compared to SISO mode. The enhancement in performance remains consistent when assessed using ADDS and ADDS AUC matrix. It's worth noting that With the incorporation of keypoints, these methods exhibit faster convergence in MIMO mode as opposed to SISO mode. We also conducted some ablation and tuning experiments. We experimented with different distribution similarity matrix and found that Wasserstein distance boosts performance more compared to others. Experiments also extend to hyperparameter configurations, including the impact of initial input, number of keypoints, and the loss components weights. In summary, we introduced KeyGNet, a network based on edge convolution designed to operate on point clouds, producing a set of keypoints with optimally distributed votes. To the best of our knowledge, KeyGNet is the first time that the keypoints themselves are learned, rather than being heuristically selected, for example using FBS. These optimal keypoints significantly enhance the performance when tested across 3 keypoint voting-based methods. Furthermore, the elimination of the SISO-MIMO gap improves the speed of these methods while maintaining comparable accuracy. Looking ahead, our future endeavors include demonstrating the impact of KeyGNet keypoints on self-supervised 6.PE methods, specifically those relying only on labeled synthetic data and unlabeled real images. Additionally, we aim to explore the potential usage of KeyGNet to generate keypoints for unseen objects without a CAD model. The extension of KeyGNet to diverse applications such as object detection and human skeleton detection is also under consideration. Finally, we extend our sincere appreciation to EarnSerc and Blueris for their sponsorship of this work. Thanks for listening. Please scan the QR code to access our implementation on GitHub.